New recording for B. Okay. So brief review and then on to something that looks more like factor analysis. So IRT models, item response theory for short, range from 1 to 4 parameters that predict the probability of a 1, and you can think of that as a correct answer or an endorsed symptom, something like that. So we have two different link functions that are being used so that we can make sure that the predicted outcomes stay within their probability boundaries. Logit is the log of the odds of the probability of a 1 for now. That's going to depend on your software package, whether it's a 1 or a 0. Probit, or ogive, is the z-score that goes with the area to the left for that corresponding probability. So you can think of it that way. There's no easy way to go back to probits, from probits to probability. You have to do integration, but normdist in Excel will do that for you. How do I go from logits to probabilities again? What's my inverse link function for that? If I have a logit, how do I turn it into a probability?
E to the logit plus over 1 plus e to the logit.
That's it. E to the logit over 1 plus e to the logit. That's my inverse link function. And we don't have any residual variances like we did in CFA. They're gone because they're not estimated quantities in categorical data. Instead, if I think about the variability of the continuous underlying distribution under my binary responses, I could say that it's 3.29 if it were in logits or 1 in probits. That's just a scaling thing. And our factor score is called theta, but it's the same idea as a latent trait. So we have our difficulty, slope, lower asymptote, upper asymptote. Okay. Now, A and B is all we're keeping for now. There is no direct translation into factor analysis for IRT models that include upper or lower asymptotes. There's no other way to estimate them besides full information maximum likelihood or the Bayesian version that adds priors to that. So we're focusing on 2 parameter models in particular from this point forward. So how would I decide if I need 1 parameter or 2? Can you guess?
Whether you believe all the items to have the same discrimination or not.
Yeah, so theoretically I could say I believe that items should be equally discriminating and I'm going to get rid of any that don't meet that. Or empirically, if you're like, wouldn't bother me if my items are differentially discriminating, how could I know that? Likelihood ratio test. Did you do this in your last homework by chance? Did you constrain all the loadings the same and see if it fit worse? Yeah, the same. The only difference is that if you're not using robust maximum likelihood, which you wouldn't need to because you're not assuming normality for the indicators in this type of model, then it's just the straight difference in -2 log likelihood. So if you put 1 in for a scale factor, the spreadsheets that I gave you would work for this. Otherwise, it's just straight difference in -2 log likelihood. So if I'm adding parameters, if it gets better or not better. So if I'm going from a Roche model, where all the discriminations are the same, to a model in which they get to differ across items, that's an example of adding things to make it better or not better. If I'm going from a model where they're all different down to a model where they're the same, which is what I had you do in homework, then that's this one, removing. So if there's a significant difference between the models, then we made it worse by adding the constraints. And we can still use AIC and BIC for non-nested model comparisons. However, and this is the thing I forgot to review last time, models with different items are not comparable. They are not. And we can't use AIC and BIC because they have as their primary ingredient -2 log likelihood. And so log likelihood is literally the sum of the multidimensional response like mountain for each person. And if I have, say, a 6x6 matrix and I figure out how tall the 6 items are for that person, and then I drop a bad item and then I have 5x5, they're not on the same scale. Like 5 is going to be different than 6 because it's 5. Has nothing to do with the models. So if you drop items, you cannot directly compare fit. Also, if you drop people, you cannot compare fit. For the same reason, it's the sum across the people, and if it's different people, then the sum will be different for that reason. So if you got that run wrong, don't feel bad. It's a mistake that's very common. Jonathan told me once he was at a conference where someone was comparing different samples, and they had like AIC values from different samples of people, and then they said, well, this one's lowest, so the model fits best in this sample. I'm like, oh no, that sample had the fewest people. That's what happened. So no, everything has to be exactly the same to use -2 log likelihood AIC and BIC. Can you think of an example of when a model would be non-nested, in which we would have only AIC and BIC? Because nested is a word that gets thrown around a lot. Not nested data, not people nested in clusters, not nested ANOVA, or nested main effects, nested models. Can you think of an example of when models would be non-nested?
You change the item from one vector to another.
Yeah, in the roomers and the zoomers simultaneously, moving an item from one factor to another. So moving it. So my way of thinking about nested is if you can add or remove parameters to get from one model to the other, they're nested. If you have to add and remove at the same time, they're non-nested. So if I have a two-factor model and I'm not sure where one item goes, if I put it on factor 1 with the loading, that's model 1. Or I could put it on factor 2 with the loading, that's model 2. To get back and forth, I have to take this one away and add that one. I have to add and remove in the same step. That makes them non-nested. Those models would also have the same degrees of freedom, the same number of estimated parameters. So you couldn't do -2 log likelihood because there's no difference in degrees of freedom. So that's an easy way to tell, is if you have two models on the same data with the same people and they have the same degrees of freedom, they have to be non-nested.
I have a question.
Yeah.
Not exactly related, but some correlating. Is that, for example, I have two versions of the same scale.
Mhm.
One contains 10 items and the other one contains 6 items, but they draw from the 10 items.
Okay, so one scale has 10 items, another scale has 6 that were drawn from the 10. Okay.
If I want to compare, so technically they should be measuring the same thing if you're doing it correctly.
Mhm.
So is there any way for me to compare those two?
So the question is there any way to compare those two? You can talk about the fit of each separately. So you can say the 10 item model has this fit, the 6 item model has this fit, and you can say whether each is acceptable, but not compare them. I think what you'd want to know is the information function comparable? So if you have 6, is it doing a good enough job?
Comparing to the information that is offered.
Yeah, I would compare the information functions or the reliability. That would be the question, I think, is 6 good enough? And in a CFA world, then it's just one number, right? Reliability was this and now it's this.
Yeah.
But in this world, it's the function.
Assuming those two versions are being filled by the same group of people on the same condition and compare those two.
Yes, you can talk about how information is different if you add the extra 4 items, essentially. That's the way I would think about it, because it depends. Like, are they all in one section of the scale where you're going to bump up like that chunk of information, or are they redundant in terms of where their coverage is? Because if they're redundant, you may not need them. But yeah, that's how I would think about it. Okay, so remember this slide. We're back. The term IRT traditionally refers to a model format that has A, discriminations, and B, difficulties. It is traditionally estimated using full information maximum likelihood, or what's known as marginal maximum likelihood. You can add Bayes to that if you want to throw in priors, but the point still holds. You're using all of the original item responses to estimate it with. The raw data. Any missing data is assumed missing at random in any kind of full information estimation. Missing at random means conditionally random after you control for the information you do have. The contrast, where we were to start, is something called IFA, item factor analysis, otherwise known as CFA for categorical responses. You will see people call it that too. And this traditionally is estimated using limited information, which is a summary of the data instead of the original item responses. Because it's using a summary, and the summary doesn't know where it came from, it's missing completely at random if you have missing data. So that's a downside. I'll put that's on a slide, but I'm going to put that front and center. Missing data is not addressed very well in limited information models. The version of the model, though, has something called loadings. Does that sound familiar? Factor loadings are back. They mean the same thing as they did before, and something called a threshold. So this is crossover time. The other class is learning about thresholds. And we're going to learn about thresholds because that's what we get, whether we like it or not, out of M+. And by the way, you can do all 4 of these combinations in M+, but in Lavaan you can only do this box right here, limited information. MERT would be a different package in R that you could use for full information. Okay, so CFA is to linear regression, as IRT is to logistic regression. We are doing factor analysis on logits, but what we have so far looks nothing like factor analysis in terms of its parameterization. Here's how we reconcile these discrepancies. So if I write a linear regression model predicting y for each item in each subject from an item-specific intercept, an item-specific slope, x is my predictor, it varies across subjects, and I have an E residual because this is a continuous response, and so we have a separately estimated residual variance. I can rewrite this equation using factor analysis notation by switching out beta 0 for my intercept, switching out beta 1 slope for my factor loading, and then everything else is the same. Okay, so with me so far. Okay, so the only difference really is x and f. X is in your data and f is not. F is an idea. A logistic regression model looks like this, where we're predicting the log of the odds of the probability of a 1. This is called logits, or log odds, by the way, and with an item-specific intercept, an item-specific slope, and x for a subject. So this part is the same. E is gone, though. Remember why E is gone when you're predicting binary outcomes? Why is there no E here? Does it mean it's perfect? It's not perfect.
The E is the other side of the probability, or how to say that? It's like that.
Say it's the other side of the probability? Is that what you said?
Or it's like for response of 1, the E is the response of 0. Does that make sense?
Yes, so E would only be 2 different values at any predicted probability. Like if your prediction is here, you're either wrong up to 1 or you're wrong down to 0. So E does not have a separately estimated variance. That's why it's not in the equation. The idea of putting E here is to represent the idea that this has a distribution. This is a random effect, so to speak. We have a distribution of E's across people. We don't have them here. Because once we know what the predicted logit is, we can turn that predicted logit into a probability, and then we know what the 2 possible E's would be. We know what the variance is at that point, so it's not constant. Then we get into this thing. Well, the first part looks familiar, yes. Non-constant variance, very good. This part looks familiar, right? And then we get this thing. So how is this the same as that? Doesn't look the same. Hang on. For whatever reason, this always returns to the middle. Every single time. And it has since I made this slide like 10 years ago. I don't know why. But that's okay. I'm going to make it work. So let me introduce you to a new thing. This is an item factor analysis model. Lambda f, that part's the same. So here's my CFA model, here's my item factor analysis model. Instead of having mu for the intercept, I have negative tau, which is a threshold. So this looks more similar in structure to a binary regression model, either in logits or probits. The only difference is beta 0 is replaced by this negative tau thing. Beta 1 is directly analogous to the loading. X is directly analogous to F. So in CFA, the loading is our discrimination parameter, and the intercept was an index of difficulty, but it's actually easiness. The higher your predicted response, the higher your intercept is. The negative here is because we're going to make it actually measure difficulty instead of easiness. We're going to flip it around. So here's how we rearrange one into the other. A times theta minus B If I distribute the A, and then I rearrange it in terms of its order to look more familiar, this is the conversion. So A is the same thing as a loading. Minus A times B, the A times B part is the threshold, and then the minus stays here out front. So when all is said and done, you can write the model this way, or that way, and it's the same. There is an algebraic transformation to get back and forth, and here's the formulas. So if you standardize your factor, if theta has a mean of 0 and a standard deviation of 1, then A is literally the factor loading. This part goes away, and you can go backwards the other way. And this becomes B is a threshold divided by a loading, or a threshold is A times B. Now, what the hell is a threshold? Do you remember how I love logits because they're symmetric? Like if I told you the logit of a probability of 1 is 4, what is the logit of a probability of 0 instead? -4. This is why. So this threshold is -1 times an intercept. The minus sign is to make it go in the same direction as the IRT model, in which this location parameter actually indexes difficulty. So thresholds are backwards so that they stay in the same direction as the B's. So this means that you can report it either way. So you can convert your loadings into A's. It's exactly the same thing if your factor is standardized. And you can convert your threshold into a negative intercept or into a location. So then you get to be strategic about how you describe your model. If you are interested in publishing for a crowd that is used to seeing confirmatory factor analysis or structural equation models, you would say, I did CFA for categorical data, and you would give them loadings, and you could give them either intercepts or thresholds, as long as you describe which one you're giving them. If you're writing for people who are used to seeing IRT models, you would give them A's and B's. But you can get from one to the other. Here's a picture that qualifies, hopefully. So here's 3 different versions of the model, okay? Logit with intercepts and loadings, logit with thresholds and loadings, or logit with discriminations and difficulties. These 3 things are equivalent. They tell you different things. So in the example I'm going to show you, this is example 1. These are the numbers from it. So the x-axis here is theta, standardized theta, and the y-axis here is probability. So this particular item has a B difficulty value of -0.376. So that is the amount of the trait needed to have a 50-50 shot of getting this item correct. And in this context, it's being able to do this item because this is an index of physical functioning. So this is like being able to take a bath by yourself or something like that. Okay, so this is B. To me, B is the most useful measure of location because B tells you who the item is for. What kind of person is this item going to be maximally informative to? And how informative it is given by A. This is my attempt at the slope of the line tangent to the curve to the best of my PowerPoint drawing ability. That is discrimination in the IRT world. It is a factor loading in the IFA world, and they are the same number so long as your theta variance is 1. So it was estimated at 4.3, so that's a very high discriminating item at this point. That's B. If I go further up the curve here, I'm going to drive up until I get to a theta of 0. This is another reference point for item location. This is where my intercept is. Intercepts, no matter what class you're in, no matter where you are in statistics, an intercept is the expected outcome when the predictors are 0, right? Theta is my predictor. So the intercept tells me the predicted item response of a 1, because that's what we're predicting, at a theta of 0. So a logit of 1.629 corresponds to a predicted probability of a 1 of 0.836. So intercepts and difficulties are different points on this curve. They're each referring to 0 as a reference, but on a different axis. So I'll say this a couple times here, and then we'll say it a few more times on Thursday. What is a logit corresponding to a probability of 0.5? What is 0.5 in probability in logits? It's 0. So another way of saying what B means is that it tells you theta when y is 0. So B tells you what theta is if y is 0. And intercept tells you what y is if theta is 0. Intercept tells you y given theta 0. Difficulty tells you theta given y 0. So I don't like intercepts because they are referring to an average person as a referent. An average person has this probability of getting this item right. Well, what about an unaverage person? Well, I can't tell you that. That's not my job. I'm focused on theta of 0. Whereas B tells you who the item is useful for. So to me, that's a much more useful measure of location, and it ties directly into the idea of reliability and information. So if I know that the logit of getting a probability of a 1 is 1.6, what's the logit of a probability of 0? Negative 1.6, and that stupid thing is a threshold. So putting it all together, if you do MERT, I'm pretty sure, Vladimir, correct me if I'm wrong, or anyone else, MERT gives you intercepts and slopes, loadings like this, slope-intercept form. M+ is going to give you thresholds and loadings form, and traditional IRT software will give you A's and B's. So your task to figure out what the hell you're doing, this is step 1. What are you getting back? Because there's 3 different versions of location. Intercepts, which are easiness parameters, thresholds, which are difficulties focused on a theta of 0, or actual difficulty values, which focus on a logit of 0. And your software may not tell you very easily, but that's where I can hopefully help. So yeah, to do M+, what we're going to do is the middle one here. We're going to get thresholds and loadings, and then I will show you how to ask M+ to turn them into A's and B's. It does it automatically for binary data. You have to write code to do it for polytomous data, ordinal or nominal. All right, 142. So do you believe me now? We're doing factor analysis. We're doing it on logits. We're right back to where we started, just with some extra crap in the middle, in the way. Questions or comments? Zoomers, how you hanging in there? You want to talk to me? No? No, rumors want to talk to
I
me?
think you might have the volume down.
Hmm?
I thought I might have. Do you have the volume down? I thought I might have heard someone.
Not that I know of. I have the volume cranked up on the recorder, it looks like, and down here and out of my face, this is my cranked volume, so yeah, that's what I can do. I wasn't a cheerleader, I was a dancer, and my job was never to yell, you see. All right, then how about we call it a day? We come back on Thursday and we can talk more about IFA and estimation. Yay, said no one ever. All right, thanks for being here. Have a good week. See you Thursday. Bye, Rumors. Bye, Zoomers. And Zach has a question.
You briefly mentioned adding Bayesian priors. Are
Yes.
we going to go over that in class, like the advantage of incorporating Bayes?
I don't have it planned, other than indirectly to say that in models that have multiple factors and you have a link function, that's when estimation can go sideways, and that's where Bayes can help because it's a brute force way of trying to figure out what your parameters are supposed to be through posteriors rather than through, numeric integration.
Okay.
But
Okay.
so I have resources, though, that I can point you towards if you're interested.
Yeah, could you?
Yes, I can do that.
Thanks, appreciate it.
Thanks for the question.
Okay, thank you, Lisa.
See ya.